Hi everyone, I'm Kumar, a final year grad student at IIT Bombay. And today at IAU, I will be talking about India's first fully robotic telescope named Growth India Telescope, which you are able to see on the left side of your screen. This telescope is situated at Indian Astronomical Observatory in the cold desert of Ladakh, and is jointly operated by these two institutes. One is IIT Bombay, and other is Indian Institute of Astrophysics in Bangalore. This particular scenery that you are seeing on your screen is the evening sky from the Ladakh or the observatory at Ladakh. The sky gets even better in the night when the sun goes down and stars come out. It's a beautiful, beautiful sky where you got about a typical thing of about an arc second, which help you in making it this one of the most promising site for optical astronomy in India. This site also gives you approximately 200 clear nights throughout the year, which is quite a remarkable thing for an observatory site. This particular telescope was set up as a part of Growth Network, which stands for Global Relay of Observatories Watching Transit Happen. So assume a scenario when one of the telescope detects a transient and you would like to follow it up for the, we would like to have a say continuous coverage for that particular target. So we know that the ground-based observatory are limited by this day and night kind of scenario in the optical astronomy. So the idea is to relay that particular target to the next observatory, which is getting something far away in the geometrical location. So as a relay race, you can again relay this target to the next observatory and to the next of that to get the continuous coverage for a particular transient that you are interested in. This is in Indian, so Growth India Telescope is also a part of this collaboration. On this page, you can see a lot of observatories which are a part of the this particular collaboration, and right in the middle of it is our Growth India Telescope. This particular telescope is India's like first fully robotic telescope, which is about 70 centimeter in a diameter, and it is accompanied by this Andor XL 230 CCD camera, which has about 16 megapixel sensor. The field of view of this telescope in combination with the camera is about um, little bit more than the size of moon, which is about 0.7 to 7 degrees. This is a simple comparison of a full moon to the field of view of GIT. Um, Looking into the science exposure depth, we got about 20 and a half mag depth in 5 minute exposure regularly in the G or R band of the optical regime. Um, Sometimes we also go deeper by stacking a number of images, and the deepest we have gone so far is about 23 magnitude in R band during the follow-up of a particular transient. Looking into the detail of how the observatory or the telescope operation works, we can briefly divide into in say three sections. One is we start with the planning of the target, where we choose a target, we decide what parameters we need, how much exposure time we need, and pass it to a code which calculates the rise time, set time, and finally prepare a list to be observed. At the starting of the night, this the telescope start with the obtaining calibration exposures and take that list that we have made by planning the target and observe all those targets one by one and keep saving everything into the database at the observatory site itself. The telescope, the scheduler handles every part of the telescope system, including filter wheel, camera, telescope dome automatically. Also, there are a few Slack bots implemented to monitor the system and to monitor all the observation independently. So there is no human intervention needed, and if there are any error or any sort of operations that could stop the observation, then it gives the call to the observer so that everything can be handled into the real time. Sometimes we are also needed to ingest additional targets apart from the list that we have made in the starting of the night. So for that, we use the TO block where we either manually ingest the target or the Slack bots that we have made to trigger the telescope automatically. They trigger the telescope on finding a suitable event like either a GRB with a good localization or any LIGO candidate during the LIGO runs. This telescope is supported by the fully automated pipeline, which again can be divided into four major parts. One is like we observe the data and download it in the real time. So all the data sits at the observatory in Hanle itself, and from there we transfer the data over the satellite link to one of the institute that I mentioned in the first slide. This is IIA at Bangalore, so this is actually connected via the satellite link to the observatory. The data is transferred to IIA, and the data can be downloaded at IIT Bombay over the internet. Um, After the data is downloaded, we go into the pre-processing of these images, where we calibrate these images and remove the artifacts in the image. And these images are now ready for the photometry, where we estimate the brightness using the aperture photometry, where we put the aperture around the object, or try to fit the PSF profile of the image to that particular object and try to estimate the brightness. In some cases, the location of the object is such that it could fall in some galaxy, so then we require some additional processing to be done, which is commonly known as image subtraction, where we take an image obtained out by our telescope and download an image from the one of the surveys. This is an image from Kansas on your screen. So we subtract those and try to find out the candidates that have popped up in the subtracted image. So you can see there's a candidate looking to be popped up at this location. But there are also these artifacts, so we try to detect the transient in the image and then try to filter out the real one from the bogus one. That's called candidate vetting. And after the human scanning, everything is verified and saved to the database on every night. So this is the typical way of data obtained and data reduction procedure with the GIP. Over the time, we were not automated at the starting of the operations, where we were observing in the manual mode for a few months, and then we subsequently upgraded to the semi-automated mode, where we implemented a few scripts and also human were handling a little bit of the task. Currently, we are in the automated mode, where everything is done by the software and the script itself, and this has led to a increase in efficiency from about 30% to the 56 in the semi-automated mode, and currently we are obtaining a regularly or an average of 85% efficiency. The efficiency is defined as the typical night spend time from -12 to 12 degree twilight, -12 to -12 degree morning twilight, sorry, and the amount of exposure that you have taken with the telescope during the full night. So a ratio of those is this efficiency. All these operations, again, I mentioned that are monitored by these bots. So there are a few bots that we have implemented which monitor the observation, the reduction, or try to trigger the data set, try to trigger the telescope. Looking into the scientific interest of GIT, we follow up these EMGW events whenever the LIGO is operational. So we look for the kilonova candidate by following up these events in optical regime. The other program involves the fast fading transients, which are discovered by other observatory but require follow-up in real time. So we follow those up and try to see the interesting targets. We have a regular program of finding afterglows of the GRBs, which are whenever there is an alert put up by high energy telescope, we try to follow up their localization and try to find the optical afterglow of GRBs. Supernova and nova monitoring are a regular program in GIT, where we follow up the different type of supernovae in the early time as well as in the late time follow up. Also, we try to follow up the near Earth objects and try to refine their orbits with the help of the GIT observations. Over the course of last 3 or 4 years since the commissioning, we have obtained quite remarkable science results, where we during the first half of the O3 run of LIGO, we obtained we followed up many events, and most of those were followed up in targeted mode, where we selected the interesting candidate and tried to follow those up. But for one particular event, we followed up it in tile mode, where we covered this North Pole cap multiple times over the course of 10 nights and tried to look for the counterpart. For the GRB program, we have followed up about 70 GRBs in last 3 years and detected 20 afterglows. Also, there have been these events where we put up the constraint of the brightness of the rest of where we did not detect any afterglow and get up to the limit of the GIT. On the supernova program, we have followed up about 35 supernovae and novae, where we covered both the thermonuclear core collapse as well as the thermonuclear supernovae. And we have followed up these for at the very starting time, as well as we followed up very late time such events. we regularly follow up these near Earth objects with GIT, where we try to follow up the asteroid, comet, and the other near Earth objects, and we have so far followed up about 100 of them. And the main purpose is to basically refine their orbits and try to make it better and better by submitting more and more observations. In the comets, we have seen a few outbursts, so we try to study these comet outbursts with GIT in collaboration with the other telescope. So this is what I have today with JIT. We are looking forward to continue this program for the upcoming years and we'll try to in just a few more programs so that the scientific results can be increased. I would like to summarize my results in the last slide where the key takeaways are basically we are obtaining a regular efficiency of about 85%, which sometimes goes up to 95% in clear nights and then nights where we don't get any sort of error from the telescope, which is quite remarkable. And all of this had happened due to the automation where we are monitoring everything in the light time and the data reduction and everything has been done in the real time. So with the help of these, we have covered these various aspects of the science, including the EMGW program, GRB, fast transient supernovae, as well as the near asteroid. And with the help of all these, we have been able to publish more than 250 referred, non-referred publications over the last 2-3 years, which is quite remarkable thing. With that, I would like to thank you for your time. If you want more information on this particular telescope, you can look at the archive paper that can this QR code, or maybe visit the website, which is the right hand QR code. Thank you for your attention. If you want to meet me, I will be present at the IAU in person, so you can talk to me if you are in touch. Thank you.